So here's the lecture I gave in class about statistics. So in AP Bio, it's a big deal. Actually, in science in general, it's a big deal. There we go. So every lecture that you get is going to have some type of focus or a focal question. That's going to be, how do we use statistics to answer questions, namely scientific questions? So here's the question that you should be able to answer by the end. So these data here were from the 2017 exam. So I had about half of the kids who took the test and the other half weren't my students. So the way you read this is mine, I had 1 5, I had 6 4s, 9 3s, 4 2s, and I had a 1. Everyone who wasn't one of mine, there were no 5s, there were 4 3 or 3 4s, there were 9 3s, 10 2s, and no one got a 1. That's right, I got the extremes. Question is, did we score the same? That's the goal of trying to figure it out. So science, what we try and do in science is we try and solve or explain, not solve, we try to explain the world around us. And we try and do that using things that we can observe and test and repeatedly test, which means we're gathering some type of quantifiable data. Not to say that qualitative or descriptive data isn't good, but we prefer numbers because we can, you don't argue over words, you don't argue over numbers, or at least you shouldn't be arguing over numbers, but you can argue over words. You can argue over how you interpret the numbers, though. And one of the best ones is the ant and the grasshopper, which is a long story that I share in class. We claim that there's this thing called the scientific method. I hate that phrase because it's not a method. Scientists do not work in this linear pattern of they pose a question, they create a hypothesis, and then they experiment, and then they analyze, and then they draw a conclusion, and then they repeat it. That's too simple. That's not true by any stretch of the imagination. Normally you have some type of observation which leads to a question. You probably try and do some background research to see if you could figure out if there is an explanation, or you take what you know, you create an explanation, you figure out how to run an experiment. Typically things go wrong during the experiment, then you say, oh wait a second, let's start over again, or you realize, oh, I'm going the wrong path, and I'm answering a question that I didn't answer or didn't ask, and it's actually far more convoluted than anything that shows up here. But let's just assume that this is what goes on. One of the things is, what do you do with that conclusion? Or what really is that hypothesis? So this table here is maybe one of the most amazing figures I've ever seen, because the term hypothesis and theory are not used correctly. So what occurs is either what we call an observation or a law. It's just what it is. A law. Evolution is a biological law. It is what it is. Observing that offspring don't happen to match their parents when there's sexual reproduction that occurs. It's not, it just is what it is. It's an observation. We're not saying why, we're not trying to explain how those things come about. We're just saying, here's what it is. The explanation part is what we either call a hypothesis or a theory. Theory being a big explanation, hypothesis being a small explanation. You created hypotheses in this class when we played Petals Around a Rose, and you also created hypotheses with the black box. You did not create any theories, because you're not explaining all black boxes ever, and you're not explaining all dice games. The catch is, how do you go from an observation to justifying, yes, my hypothesis works, or no, this hypothesis doesn't work, or do these collective sets of data justify what occurs in this theory or within the hypothesis? And that's where the realm of statistics comes in, because there's variability built into almost everything that happens. There's chaos. This is a fun figure just because not a lick of it makes any sense, because that's the world of statistics. There are lots of tests that exist, and for the most part we're going to ignore most of them. I'm going to just focus on a few tests that we're going to use in this class. One of them is what we call the t-test, or the student t-test. And what you do with the t-test is you compare two different groups, and you're saying, hey, are the groups similar or are they different? That's all we're trying to do. This link right here will actually allow you to actually enter in your data, then it will run the analysis for you. I'm not going to tell you how to interpret it because it's actually not as nice as we would like it to be. There's actually about 4 or 5 different equations for the student t-test. So it turns out we have a workaround, and that's something called the standard error of means. So what you have is if you were to take different groups and if you were to figure out their mean values, so their average but mean meaning or implying the entire population. So if you were to take those average values and plot them in a bar graph, the thing is, with those values, there's a bit of randomness that's fit in. And statistically, we can measure that through something that we call the standard error of means. There's an equation that goes with it. The equation is awful. It's going to be on your purple sheet. There are workarounds to not doing it by hand. In class, I show you the equations here. I'm not going to do it to you because you don't need it. But what you can do is you can take the mean and you could take 2 standard errors above it and 2 standard errors below of it. And what this tells you is 95% of the time, the mean is somewhere within those bars. Within those error bars, we have the truth. So for our one sample, we have our lines for where the means are. But based upon the data, we can actually calculate where it could be. So 95% of the time, it's going to be within that range for group A. For group B, it's going to be within that range. For group C, it's going to be within that range. For group D, it's going to be within that range. To which you say, why do I care? Well, if the real answer is somewhere between these two, it is possible, if I look at groups A and B, even though you look at the 2 means and you say, oh yeah, they're not the same. Well, if I look at the error, which is saying where I could find the answer, the 2 error bars overlap. So we have this section of overlap right here. The result is they could be the same. Within 95% chance, they actually could be the same. If I look at C and D, the error bars don't overlap, which means they can't be the same. C and D, 95 times out of 100, they are different. The other 5%, I'm not so sure about. But we can adjust the error bars to figure that out. Graphing is so much easier. There's another type of test that you can do in terms of statistical testing. Square. I know it says chi, but it's pronounced chi. It's a Greek letter chi, from which we get like a chiasm or chiasma or things like that. It looks like an X, but it's not an X, it's a chi. What this thing is, it's a test of, is what I expect reality? So this is testing probabilities. So you expect, if we look at how genetics works, you should expect half of the children to be boys, half of the children to be girls. That's because it's an X and a Y, so it should be 50-50. The question is that really what happens? So the chi-square test is one way that we can actually figure out, is reality what we expect? We're actually going to use it quite a bit, and like I said, it's the second half of the week, which you will be starting. Linear regression looks for correlations. Correlation is not necessarily a causation, although we can use plenty of correlations to rule out or to generate a causation, but that's a far different story for a different time. I'll probably link the video for that one somewhere. It's actually a fascinating little video. But what correlations do, or a linear regression, is we have a whole bunch of discrete data that we can mathematically link, potentially. And what we do is we use a mathematical trick called an R-squared value, or a Pearson coefficient. And what you can do is, based upon how all those data look, it's either, you use the computer to do this, it will generate what we call an R-squared value. If it's a 0, we're saying, there's no real pattern to it. The closer I get to plus or minus 1, I'm saying there's a pattern. Plus 1, it's a positive slope. If it's a minus 1, it's a negative slope. But regardless, the closer we get towards a 1, or absolute value of it is a 1, we're saying, hey, there's a pattern. pattern does not necessarily mean causation, meaning one variable is causing the other. The X or the independent is triggering the Y or the dependent. All of statistics, we actually create what we call hypotheses. A hypothesis is just an explanation. And there's two in the world of statistics, or at least for our version of statistics. So if you take AP Stats, I'm giving you the super simple version. The null hypothesis is the starting point. So I would start with, if I were doing a t-test or comparing groups, they're not going to be the same. Or, pardon me, there is no difference. So the groups are the same. For chi-square, we're saying, yeah, you're matching the pattern. So what I observed is what I expect. Or if you're dealing with a regression line, what you're saying is, yeah, there's going to be a pattern. The alternative hypothesis is, oh, the groups aren't the same. Or, no, the patterns didn't work. Or, I need to come up with something else because this line didn't turn out to work. How I try to generate the line is wrong. Maybe it shouldn't be linear, maybe it should be exponential, or a power function, or logarithmic. The null hypothesis is the default. It is the easiest possible answer, which is, yeah, the groups are the same, because I don't need to explain that. Or saying, yeah, observed is equal to expected, because I don't need to explain that. Or, yeah, we can explain it with a line, or with the general line, because I don't really need to explain that. The alternatives, I now need to come up with a different way of explaining it. That's why it's the alternative hypothesis. What you do is you perform the math. That's what we call a test statistic. So that'd be a t-value or a chi-square or the r squared, the Pearson coefficient. And what you have to do is compare that with a value that you look up in a table that we call the critical value. And I'll show you how to do that in class. It's not too difficult. It's looking up something that we call the degrees of freedom, which is the flexibility that you have in figuring out numbers. For our case, it's the number of items minus 1. And then you look up something called a p-value, which is how confident are you with your answer. And p-values there would be like, you say you could pick a p-value of 0.05, which is saying I'm okay being wrong 5 times out of 100, or 0.01, I'm okay being wrong 1 time out of 100. I'm being super simple and generalizing, so when you take AP Stats, know that I'm generalizing. And we'll practice this in class. So I gave you a puzzle at the start. So which test? I gave you 3 tests. Which ones would you use? Would we need to make a graph? Do we not need to make a graph? What hypotheses would we have? What conclusions would you draw? That's what we did in class over the course of a week.